Okay, so what we go over today is mostly going to be a review. In fact, it's probably going to feel like we're taking a step backward because we've talked about mechanical energy already, and mechanical energy is made up of kinetic and potential. But it's still important to talk about kinetic and potential energies on their own, just so that we understand what kind of things can influence and affect them, because that stuff also then influences and affects mechanical energy. Okay? So, in this unit, the type of potential energy we are going to deal with is gravitational potential energy. Okay, we'll deal with elastic potential energy when we get to unit 4, then we deal with springs and things like that, because it fits better with that. Right? So, if something is going to have gravitational potential energy, that is energy due to position. Okay? That position has to be somewhere where there is the potential to do what? Fall, exactly. Okay? It has to be above the ground. Okay? There has to be the potential for it to fall and convert the potential energy that it has into kinetic energy. Okay. Can potential energy do work? Nope, it can't. It could if it gets converted into what? Kinetic. Okay, right now, sure, this coffee cup has potential energy. It could fall off the desk. But it can't do any work in this condition. It can only do work once it gets moving, gets kinetic. Okay, that's the only time it can actually do any useful work. So the thing about potential energy is it's great to have it, but you still have to convert it into something else in order for it to be able to do anything. Okay? Now, for gravitational potential energy, okay, there's really 3 things that can affect it. Okay? And those are the 3 things that are in the formula for gravitational potential energy. Okay? We know that the change in gravitational potential energy is going to equal the work done to get it to whatever position it is now in. Okay? We know that work is force times distance. We talked about this the other day. What force do you work against when you're giving something gravitational potential energy? Gravity. How do we calculate the force of gravity? Well, we may or may not, but how do we calculate it usually? Mass times gravity. Okay, and the distance over which we do this work is a vertical distance. What do we call a vertical distance? A height. So that's where this formula comes from. It's the force of gravity times distance, and a vertical distance is a height. Okay? So that's why m times g times h works and gets us joules and represents gravitational potential energy. So these are the 3 things that could affect the gravitational potential energy of an object. And these 3 things are something we understand innately. That means we're kind of born with this understanding of these 3 things. Okay? So for example, let's say there's 2 cranes. Okay? And these 2 cranes are holding up 2 different objects at exactly 10 meters above my head. Okay? One of them is a tennis ball, for whatever reason. And the other one is a piano. Am I innately more afraid of the piano? Yeah, I have an instinctual fear of the piano. I don't have an instinctual fear of the tennis ball. Even though these are 2 man-made objects and there's no, caveman me would not have, understood what a piano and a tennis ball are, but looking at them, I know one is dangerous. Why is the piano more dangerous? It's bigger. It has more mass. Okay? It's something we understand innately. Big things can hurt us. Little things are less worrisome. Okay? Now, that of course falls apart when you're talking about little things like scorpions and spiders and stuff like that, but okay, that's different. Okay? This is mass. Okay? We understand that big things are dangerous. Okay? Now, I said they were both 10 meters off the ground. Okay? So they were the same height off the ground. Even if the tennis ball falls and hits me right in the head, it's not going to hurt me too badly. Okay? But height is another thing. Okay? If that piano is on the ground, I'm not afraid of it anymore. Okay? Because it really can't hurt me. It's on the ground. It can't fall any farther. Okay? It's now not dangerous anymore because it has no ability to do anything except sit there and maybe play music if the right person sits in front of it. Okay? Not me, because it would just sound awful. All right? Now, the other thing is gravity. Now, we don't really have an innate sense of that because we evolved in one gravity environment, okay, where gravity was 9.81 meters per second squared. But would that piano be as scary if it was 10 meters above the surface of the moon? It'd still be a little bit scary, but it wouldn't be as scary because on the moon, it would weigh 6 times less than it weighs here, which means it would have 6 times less potential energy at that point. Okay? And it would fall really slowly. I would have time to get out of the way. Okay? You drop something from 10 meters on Earth and you have a split second to react. Okay? But you drop something from 10 meters high on the moon and you can go and jump out of the way and not have to work. Well, in your spacesuit you'd probably be a little less mobile than that, but okay, it's going to fall a lot more slowly. All right, so does that sort of make sense why those three things are going to affect the gravitational potential energy of an object? All right, so that's the big thing we got to understand. Okay, EP is m times g times h, mass times gravity times the change in height, or just whatever the height is measured from the ground. Okay, so anytime an object's moved upwards, height increases, okay, and we increase the gravitational potential energy of the object. Okay, so super simple calculation here. If I want to calculate the potential energy of the people on this ride, which is like the space shot, okay, at West Edmonton Mall, right, or how it used to be, because they're like taking everything apart now. They're taking the Mindbender out. Did you guys hear about that? We're never doing the West Ed trip ever again now because they're taking all the cool rides out. Okay? No point even going anymore. So if these people are 48 meters above the ground, okay, and the car has a mass of 500 kilograms, okay, I can pretty quickly calculate how much work would have to be done to lift them there, and thus how much gravitational potential energy they would have at that point. Okay, so I just take 500 times 9.81 times 48 meters. All right, is that a lot of energy? It is. Yeah, I wouldn't want to stand underneath that. Okay, that's a lot of energy. That can do a lot of work. Okay, that also means it was a lot of work to lift it there. Okay, there's pretty heavy machinery that does that kind of work. Okay. All right, so we would have 235,440 joules. We only have 3 significant digits, so 2.35 times 10 to the 5 joules. Okay. Okay, if this happened in the perfect physical world, how fast is the cart going when it gets to the bottom? As this thing falls, what happens to the potential energy? It converts to kinetic. So would the kinetic at the bottom be equal to the potential at the top? Okay. So could I say this then? Would that be true? That's the law of conservation of energy. We're going to talk about that next week. You've done it already in Science 10. Okay? All right, here's the good news about that. Mass is on both sides, so it would cancel. Divide both sides by 1/2. Take the square root. Okay? Not a very mathematically challenging question, right? But we can certainly solve for how fast that thing would be going. Okay, so 9.81 times 48 divided by 1/2. Okay, that's a fun ride. By the time you're getting to the bottom, you're going about 112 kilometers an hour, something like that. Okay, that's pretty fast. Okay. Anyone ever ridden the space shot at Westhead? Okay. The one that shoots you up and then shoots you back down, and it's fun. Okay. And we actually had at one point, they got in trouble for this. They actually got kicked off the ride because they're not supposed to do it. But one of our students, when we used to go, put a penny, that tells you how long ago it was, okay, in his hand. And when he got to the top, the ride stops. But it was a perfect example of Newton's first law, because they snap a picture of you at the top, and the penny was hovering right in front of his face in the picture. Okay? Because he stopped and the penny kept going. Now, for obvious reasons, they got kicked off the ride. You don't want a penny getting in the machinery on which people's lives depend. Okay? And they're like, he's like, well, I didn't do anything. They're like, Exhibit A, the picture of you with a penny floating in front of your face. Okay. We bought the picture anyway. It was poor. It was a very poor lesson. Yeah. Okay. Yeah. So it looked pretty cool. Okay. Does that make sense? The potential energy part. Okay. So in this situation here, okay, we got a toy car at the top of this apparatus here. There's a track, and a block, and a table. Okay. We want to calculate the gravitational potential energy of the car, which has a mass of 0.0250 kilograms, okay, relative to the floor. Okay, so in its current position, it is 2.15 meters above the floor. Okay, now this is the key part here. Whenever you're calculating potential energy, you need a reference point to measure your height from. Most of the time, it's, common sense, it's the ground or the floor. Okay? But once in a while, it'll ask you relative to the bottom of the track. And the bottom of the track in this question is still 0.950 meters above the floor. Okay? So sometimes they do that, you just have to watch out for it. They will always tell you relative to this or relative to that. If they don't, then you go with the ground. All right, so relative to the floor, I want to calculate the gravitational potential energy of that car. So m times g times h, right? So we take that 0.025, we multiply it by 9.81, and we multiply it by the height, 2.15 meters. All right, is that very much energy? It's not. It's a very small car. The mass is very small, so it's not going to have a lot of energy. It's not going to have a lot of ability to do work. You'd easily be able to reach out and stop it, okay, when it's coming down. So there's our potential energy, okay, 0.527 joules. Okay. Now, calculate the change in gravitational potential energy of the car when it arrives at the bottom of the hill. Okay, so how far is the bottom of the hill from the floor? 0.950 meters. So if I want to calculate the change, okay, change in anything is final minus initial. Did I already calculate the initial? Right? This is the initial right here. This was at the top of the track. So I already calculated that. Right? So all I have to do is go 0.025 times 9.81 times now the height at the end of the track, 0.950 minus 0.527. Okay, is this going to be a negative number? Yes. The energy it has at the bottom, the potential energy at least, is less than the potential energy at the top. It's losing potential. Is it losing mechanical? Because all of the potential is turning into kinetic. Okay? That was like question number 1 on the quiz the other day, right? We said the mechanical energy actually doesn't change because in that situation the potential became kinetic. Okay? All right, so we're going to have our 0.025 times 9.81 times 0.95. Okay, and then we'll go that one minus that one. All right, so we get negative 0.294 joules. Okay? And it's okay that it's negative because it does have less potential energy on the tabletop than it had at the top of the track, okay? Because it's now lower. All right, everybody okay with that? Okay, I would like you guys to try question number 1. Okay, now, a pile driver is a tool, not the wrestling move. Okay, the wrestling move very closely resembles what a real pile driver does, which is probably why they named it that. Okay, but a real pile driver is a big heavy weight that is lifted up really, really high and then dropped onto a post or a piling and drives it into the ground. Okay, they use it when they're building like big buildings, like in downtown Calgary when they were building the Bow Center, okay, and stuff like that. You could, if you walked by there while they were doing the initial stuff, you'd constantly hear a banging sound, and it was these pile drivers that were pounding the pilings down into the ground below the frost line. Okay, all right, give you some time on number 1. Okay, let's have a look at this one here. All right, so relatively straightforward. We're trying to find the gravitational potential energy at its highest point and lowest point. It's the same calculation for both. Okay, so EP at let's say point 1, which will be the highest point, m times g times h. All right, so we take our 550 kilograms and we multiply it by 9.81 and we multiply it by 12.5 meters because they did ask relative to the ground, not relative to the lowest point. Okay, so we punch all that in. Okay, so 550 times 9.81 times 12.5. Okay, so there's our potential energy at the maximum height, 67,443 joules. Okay, potential energy at the lowest point, same calculation, m times g times h. Okay, 550 times 9.81, but this time we use the height at the lowest point, which is 2.3 meters. Okay, so 12,409 joules. Okay, and if I want to find the change, all I do with those two numbers is subtract them, right? So nothing terribly challenging for you there. Okay. So actually it should be, what does it say, which order? Gravitational potential energy when it's lifted. So this is the final minus the initial. Okay, so it's a positive change because we are lifting it from a lower height to a higher height. Okay, so if I had asked you how much work is done to lift it there, would you already be done? You would. Because work is a change in energy. There's no change in kinetic energy here. It doesn't mention anything about accelerating the piling or the pile driver. Okay, it just mentions about lifting it. So yeah, that number right there, the 55,034 joules, would be the work done lifting the pile driver from the top of the piling to 12.5 meters. Okay, so it's important to understand that definition, right? That definition of work. Work is a change in energy. There's a whole bunch of ways I can word a question to ask you whether you understand that. Okay. I want you to try number 3. I'll give you a few minutes on number 3. All right, so on this one here, okay, we've got a winch and it's pulling something up this 20-meter long ramp. Okay, that is angled at 35 degrees. Okay, if I want to find the change in gravitational potential energy, I'm going to assume that it starts at the bottom and ends up here at the top. Well, that means it has no potential energy at the bottom. I can find its change in potential energy by going m times g times hf. This would be my final height. Rather than going through the whole effort of calculating fg and f parallel and all of that, okay, this is 2 steps, 2 pretty easy steps. Okay, so I've got the sine of 35 equals, okay, the final height, which is the opposite side, over the hypotenuse, which is 20 meters. So I just bring the 20 meters over here by multiplying, and I'll have my final height. All right, so sine of 35 times 20 And it tells me that that side is 11.47 meters. Okay, and now I can just plug into my formula here. So 250 times 9.81 times 11.47, and I'll have the change in gravitational potential energy. All right, so we're looking at 2.81. We have 3 sig digs, yeah, times 10 to the 4. Are you okay with that one? Okay. So, would that also be the amount of work done by the winch? Assuming the ramp is frictionless. It would be. Okay, there's no change in kinetic energy. It doesn't mention the object is accelerating. Okay, so that would be the work done. It would be the change in the mechanical energy also of that object. All right, kinetic energy. This is another thing that we have an innate sense of. Okay, if I've got, something small moving towards me at 5 meters per second, let's say it's a bug. Okay, I mean, I might be afraid of it because it's a bug. Maybe a bug's a bad example. I have like a 1 gram piece of dirt, or marshmallow, yeah, flying towards me through the air at 5 meters per second. Am I terribly afraid of that? Probably not. It's not going to hurt me. Okay. If I have a semi-truck approaching me at 5 meters per second, am I a little more afraid of that? It's got more mass, right? It's this thing about mass. Big things are naturally more intimidating to us. Okay. Now, what if the semi-truck is moving at 0.05 meters per second and the marshmallow is moving at 300 meters per second?
Not going to be a lot you can do.
Not going to be a lot I can do. I'm going to have marshmallow on my face, okay? And it's, not going to be cool, okay? But this is the idea. Fast-moving things have a lot of energy, even if they're small, okay? Because if we look at the formula for kinetic energy, it's 1/2 mv squared. Which part, mass or speed, has a bigger effect on your kinetic energy? Speed. It has an exponential relationship with kinetic energy. The faster you go, you will have exponentially more kinetic energy. That means if you double your speed, you have 4 times as much energy. If you triple your speed, you have 9 times as much energy. It doesn't take long before even small objects can have a lot of ability to do work.
So is your potential, like, let's say you're at the top of a cliff, standing on the top of a cliff, is your potential energy just what your kinetic energy would be if you were to jump off the cliff?
If there was no friction, no air resistance, if you jumped off the cliff, then when you got to the bottom, your kinetic energy would equal the potential you had at the top.
Okay.
Yeah, you missed that. We actually went over one like that.
Oh.
Yeah. Okay, so for kinetic energy, okay, the big thing we have to remember here is that the relationship between kinetic energy, which is your ability to do work, okay, and speed is exponential. This is something people forget all the time. Not if it's something approaching them, it's very obvious. There's no avoiding that innate, evolved kind of reaction or sense of that. But they forget it when they're operating a vehicle that's moving at a high rate of speed. Okay? Why do you think there are special speed limits for playground zones, school zones, and construction zones? Okay? It's because speed has an exponential relationship with the amount of energy your car possesses. Okay? Now, here's the other thing you need to realize, and I don't know why they don't really teach you this in driver's ed, but if I want to stop, I have to turn all of my kinetic energy into what? Well, if I slam on my brakes, they don't turn it into potential, they turn it into
Mechanical.
heat and light and sound and all the other things that represent my kinetic energy not being there anymore. Okay, that's what my brakes have to do. So they have to do work. That means they exert a force over a distance in order to change my kinetic energy. Okay, now, we're assuming that in a situation like that, that my final kinetic energy will be what?
0.
0, because I'll be stopped. Okay? So essentially, the work that your brakes have to do is equal to the amount of kinetic energy possessed by your vehicle. That means, since this number is predetermined and there really isn't anything you can do about it, it's how good the road conditions and your brakes and all of that stuff are, that distance has an exponential relationship with your speed. The faster you go, the farther you will travel before you can stop, exponentially. So if you're going 30 kilometers an hour in a playground zone, you will stop in a certain distance. If you go 60 kilometers an hour through a playground zone, it will take you 4 times that distance to come to a stop. That's big. Okay, and I can prove it to you mathematically here. Okay, it's pretty simple math. So let's say, we'll deal with the first situation. Let's say you're going 30 kilometers an hour. Okay, so take our 30 and divide it by 3.6 to get it in meters per second. Okay, so 8.3. So we're going to say this. The work done by my brakes is equal to the kinetic energy that my car possesses. Okay, let's just say, to pick kind of a fairly accurate number, that my brakes can exert 10,000 newtons worth of force to stop my car. That would be a combination of the brakes and the friction between my tires and the road and all those things that help me stop. Okay, so F is going to be 10,000 newtons. I want to solve for how far I'll travel in my car that's, let's say, 2,000 kilograms. Okay, so we got mass, okay, and we got force, right? We're solving for distance, and we know that V is the speed limit of 30 kilometers per hour. Okay, so if I want to solve for D, I just divide both sides by F. Agreed? Okay. So at the speed limit, it's going to take me just under 7 meters to stop. Okay, so
And
that far.
That's going 30?
That's going 30. Okay, now it's a heavy vehicle, 2,000 kilograms per heavy. It's probably a truck more than a car. Okay, but yeah, the more mass you have, obviously that makes a difference too, right? All right, now let's say that the person driving, because it's not me, because I'd never go 60 through a playground zone, is a complete idiot and is going 60 kilometers an hour through the playground zone. And as a result, are going 16.6 meters per second. Okay, so all we do is we switch out the 8.3 for 16.6 squared. All right, so 0.5 times 2,000, because it's the same car, okay, times now that number squared, divided by the braking force. Still the same car, so still the same amount of braking force. Okay. Oh, I forgot to square it, didn't I? Yeah, I forgot to square it. 0.5 times.
How do we know the braking force is 10,000?
I just picked a number. It's a fairly reasonable number. Squared. Oh no, that's right. 5 by 10,000. Okay, no, that's 4 times. That's 4 times 7. Okay, I don't know what I was thinking of, but that's 4 times as far. That's 27 meters now. That's like the length of this room, the hallway, the lab, and a little bit more. Okay, that's a big difference. Okay.
Is that even like slamming on the brakes completely? Like putting
Yeah, we're saying like under ideal conditions,
Right.
we'll say. Okay? Is that a big difference?
Yes.
It certainly is if a kid runs up in front of you. Okay? There's a huge difference. Now, obviously, nobody would do that. We'll say nobody would do that. There's, a very small percentage of the population that does really stupid things. Okay? But we'll say nobody would do that. But how often do we say to ourselves, 10 kilometers an hour over the speed limit's not a big deal?
Yeah.
We all do it, right? I don't do it in a playground zone because I have kids and I understand this relationship because I teach physics. And after today, so will you. Okay? 10 kilometers an hour doesn't seem like very much, but it ends up being a lot. Let's go back to this example. Let's say you're going 40, because 40 is not that much different than 30. It's only 10 kilometers an hour. Okay? So 40 divided by 3.6, 3.6, right, is now 11.1 meters per second. Right? So if we flip this whole thing again, okay, now we swap out 16.6 for 11.1 squared. Okay, so we go 0.5 times the mass of the car times that speed squared, okay, divided by the braking force. Okay, 12.34 meters. So we went from 6.9 meters to 12.4 meters. We only increased our speed by 10 kilometers an hour. Okay, it's like 25%. But I almost doubled my stopping distance by doing that. Okay, that's that exponential relationship. The faster you go, you have exponentially more energy. And it will take you exponentially longer to stop. Okay, so that 10 kilometers an hour is big. It's an extra 6 meters of stopping distance. Okay, so from my desk to just in front of Devlin there was what is how far it would take me to stop going the speed limit. Okay, now go all the way across the hall and into the lab a little bit, and that's how much it would take me to stop only 10 kilometers an hour faster. Okay, now we all do. Okay, we all go, 10 kilometers an hour is not a big deal. Okay, and we think we're saving all kinds of time by doing it. Okay, but here's the thing, guys. A typical playground zone is about 250 meters long. Okay, so if I'm going the speed limit, okay, and I figure out the time, so D over V, 250 over 8.3. So if I go the speed limit through a playground zone, it takes me 30 seconds. If I go 40, it takes me 22 seconds, well, 22 and a half. So I save myself a grand total of 7.5 seconds.
If you go in the speed limit, it takes you 22 seconds to stop.
No, that's how long it would take me to go through the playground zone.
Oh.
If I went 40, it would take me 22 and a half
Oh.
seconds to go through the playground zone. If I go the speed limit, it takes me 30 seconds to go through the playground
So
zone.
you're only saving it, yeah.
7 seconds, 7.5 seconds. Okay, now, here's the thing they'll never teach you in driver's ed. And I don't know why, because it teaches the responsibility of operating a motor vehicle. If you go 40 through that playground zone, you're saying that your 7.5 seconds are more important than a kid's life. Okay? If that 7.5 seconds is going to be the difference for your life, understand it's going to be the difference for somebody else's life. Okay? It's the difference between I have dinner with my kid or I plan his funeral. Operating a motor vehicle is a big responsibility because there's a lot of energy involved in a moving vehicle. They're big, they're heavy, okay? They have a lot of ability to do work, okay? And that's something that we sometimes forget because it's just easy to point it down the road and steer it and do whatever. We kind of forget just how dangerous they can be. Okay, so you got to keep that in mind when you're driving. And I get it. At your age, it's not something that maybe is a real part of your world. I know it wasn't when I was your age. Okay, but once you have kids and you're a little older, it's like, man, a lot more things feel dangerous. Okay, you get this totally different sense after you have your own kids of what things are dangerous and what things aren't. I used to rock climb and mountain climb. Then I had kids, I can't even get up on a mountain and look over the side anymore. I just can't. Okay, it's like if I fall, my kids don't have a dad. Okay, like it changes your life. Okay, let physics change your life in a good way. Make you think when you do things. Okay, like go 40 kilometers an hour through a playground zone. Don't do that. Okay, it's 6 meters difference. It's a big deal. Rant over. I stayed much calmer that time. Sometimes when I give that rant, I get like red in the face and upset. Okay. So on this one here, we're looking at, again, this is this relationship between mass and speed. So on a highway, you've got a car that's 1,200 kilograms going 20 meters per second. It has the same kinetic energy as a loaded van that is 4 times heavier. Okay? What's the speed of the van? So the van's 4 times heavier, but has the same energy. What's an estimate for how fast the van's going?
Not that fast.
Not that fast. Half as fast?
Quarters.
Well, I don't know if it'd be a quarter, because we got that exponential relationship.
Oh.
Right? They have the same energy. One is 4 times heavier.
Yeah.
So it's probably going half as fast. Well, let's check. Let's make sure. Okay? So what we're going to say here is that 1/2 the mass of the car times the speed of the car squared is equal to 1/2 the mass of the, let's say truck, because I don't want to put V in there twice. Okay? Speed of the truck squared. We know they're equal. Okay? We're trying to find the speed of the truck. All right, so I'm going to divide both sides by 1/2 times the mass of the truck. Okay? The halves are going to cancel. Okay? You'll be left with the square root of the speed of the truck. So, okay, do that and I'll have it. Okay, so 1,200 times 20 squared, okay, divided by 4,800. Whoop, not second log. Yeah, well, what's the square root of 100? 10. Is that half as fast? Yeah, it is. 4 times more mass. You go half as fast, you have the same amount of energy. Okay? So if you're driving something big and heavy, like maybe you're going to become like a long-haul truck driver, and you're going to, be hauling a big B train full of goods. Okay, a B train, by the way, is one big long semi-trailer followed by another semi-trailer. Okay, so it's a trailer behind a trailer. Okay, that's a lot of mass. Okay, and it's going to take you a long time to stop that. Okay, because you get more energy because you're so much heavier. All right, we will leave it at that for today, okay? And we'll pick up with more energy stuff on Monday.